Okay, so thank you for having me. Thank you for the organizers for putting together a great agenda. I've got 40 minutes to talk to you about contrails and explain what they are, why they impact the climate, and what we can do about them. So I could easily fill 2 days with this presentation, but I'm going to try and condense it. Much of what I show will be familiar to a lot of you, but I'm hoping that this is accessible to a wider audience. We will have some time for some questions. This is a picture I took from my garden at home. Right? So Joachim gave the story of how 3 years ago he became interested in contrails because he saw the opportunity. Well, back in 2015, we were working on looking at aviation emissions and how those aviation emissions affected or how they were uncertain, how we didn't really know about what quantity of emissions were coming out of aircraft engines. Right? So we then thought, oh, wouldn't it be interesting to understand that uncertainty and its effect on contrail radiator forcing uncertainty. And that's where we came at this problem, is there's uncertainty in emissions, so there's going to be uncertainty in contrail radiator forcing. What we then discovered as we went through the process of doing the research and modeling of contrails is that actually a very small fraction of flights form the most meaningful contrails, regardless of the emissions uncertainty. And that's because of the way that contrails form and the critical dependence on the environmental conditions, on the ambient conditions. So 10 years ago, I had that same experience that Joachim was describing there, where it was like, oh, wow, this could be something that changes the way we think about planning flights, think about aviation and its climate effects. And I show this picture because now my 2 kids know what these are, right? So they point up at the sky, they say, oh, there's a contrail there. And in some ways, that tells us that this is the most visible effect that humans have on climate change. Not just of aviation on climate change. It's not just more visible than, say, CO2, but potentially I think there's an argument for saying this is the most visible impact that humans have on climate change. So we know that contrails will sometimes be in the sky, and sometimes, like today, you can't even see the sky. So we can't see the contrails even if they're being formed. But on specific days, we see lots of contrails, right? But even in this image, as you see it, you'll see some aircraft fly across the sky. Some of those aircraft are forming contrails, some of them are not forming contrails. So why is that? We'll unpack that a little bit. So some of them are flying slightly higher or slightly lower at different altitudes, right? And they're avoiding regions of the atmosphere where contrails are going to form. We can also see contrails in satellites. So from this is geostationary satellites, and what we're going to see over Dallas is a contrail outbreak, and that is being advected by the wind, and there's clearly contrails that are being formed there by flights in that region. But you can see just around it, say to the north of it, there's no contrails. Over time, those contrails kind of spread out and they then disappear as those contrails kind of reach the end of their lifetime. But in this image, they're contributing to the what we can see, so we can observe these as clouds. But we also know in that case, then they're also affecting how much heat is being able to escape from the Earth out to space. Now, this is one of the most sort of visible examples of how contrails do turn into clouds. So we've got a military aircraft that had a flight that was in a sort of circle to the east of the north of England, which you can see in the top left-hand figure. And then the next images are images taken at points in time after that initial figure. What you can see is that contrail, that initial circular contrail, well, it actually looks like a spiral because it was being advected as the plane was going round in a circle, travels down towards London and the southeast of the UK and contributes to, along with other contrails and some other cirrus cloud, very high-level cloud that sits over the top of southeast England. So what we understand is that emissions from aircraft lead to and contribute to the formation of contrails. Some of those contrails will persist. They will have a radiative forcing effect. So that means they trap outgoing long-wave radiation or outgoing heat, and they also reflect sunlight. So for every contrail, there's this balance between how much heat it's trapping and how much sunlight it's reflecting back to space. And then eventually the contrail disappears, so we have a blue sky again. And what we understand about emissions, so we're going to step through these phases, is that the particles that are emitted by aircraft engines contribute to the location, so they provide a location onto which ice can form. So the emissions of particles from aircraft engines nucleate water droplets. Those water droplets, within about a second or a few seconds, are able to freeze into ice particles. And then if the conditions are right, if it's humid enough, then those ice particles will continue to grow over the period of a few minutes. And that's what we see, right? We are seeing a cloud made up of ice particles. Now, if we look further into the emissions, we know that there's different types of particles emitted by aircraft engines. We have what we call non-volatile particulate matter, which is another word for saying soot particles. So those are the sort of black dots. We also know that we have volatile particulate matter. That could be condensed organic material that might come from unburned fuel, but it could also come from lubrication oil that is put into engines to obviously lubricate the engine, that could escape and be vented out into the aircraft plume. There is also a very low concentration of ambient aerosols, which are entrained within the plume and could also be within the plume. And as that plume cools, the water vapor that comes from combustion reaches supersaturation. So it wants to form droplets. It wants to condense onto a surface. So you have a droplet then formed onto a soot particle, a non-volatile particle, or a volatile particle. So conventionally what we've understood is that with conventional kind of older generation aircraft engines is that the non-volatile particulate matter is the particle of interest, is the main cause, the main source of the contrail ice particles. But as we are reducing the number of those particles, the other particles become important. Right? We're reducing the non-volatile particulate matter by changing fuels or changing engine technology. And in that case, then, the other particles are starting to take its place. So we're sort of trying to understand what the effects of the change in emissions will be on contrails. And this is sort of a schematic showing that if we have lots of soot particles around, then they are going to really drive the formation of ice particles in the contrail. But if we reduce the number of soot, then maybe we end up with fewer ice particles in the contrail. Because there's fewer ice particles for the same amount of water vapor that's condensing onto them, those ice crystals grow to be larger, which potentially means that they have a higher sedimentation velocity. They fall out of the atmosphere more quickly. That means the contrail doesn't last for as long. On the other hand, though, if we start to activate these volatile particulate matter particles, or these other types of aerosols in the plume, we could end up in the situation that actually it's not very different. The low soot, if we're able to reduce non-volatile particulate matter, because other particles take their place, we end up with the same situation, right? We have a similar number of ice particles in the contrail plume. What we're finding out is that this is, as I'll come to show you, dependent on the ambient conditions. But so the takeaways in terms of emissions are the engine particle emissions modify the properties and lifetimes of contrails, and the fuels and technology can reduce those emissions. We've conventionally thought that non-volatile particulate matter is the only thing we need to be concerned about, but actually there's greater evidence that we need to be concerned about all of the particles emitted by aircraft engines, including volatile particulate matter. Unfortunately, volatile particulate matter is not routinely measured. Right? In fact, it's explicitly excluded from the regulations today. So that's something we need to develop standards for, and more measurements are needed there. And it also means that sulfur content of fuels is likely to become an important topic again. And so what, right? So engine emissions of total particles need to be considered, and it's likely that sustainable aviation fuels, while they might reduce non-volatile particulate matter, they're unlikely to eliminate contrails completely. Right? So I think that's an important point. Some people do say that with sustainable aviation fuels, that the contrail effects are going to go to zero. Well, that's not the case based on the evidence. And there's a bit more on that later. So from emissions, then we have formation. So we have to form a contrail. So again, in this situation, you see some aircraft flying across this screen, and some of them are forming contrails and some of them are not. Right? So why is that? And it really is because you need the plume to be sufficiently humid. You need enough water vapor in the contrail plume to want to condense onto really tiny particles emitted by the aircraft engine. And when I say tiny, they're sort of tens of nanometers, a few nanometers to tens of nanometers in scale. And so you might have heard, or you may come across the term the Schmidt-Appelmann criterion, which is explaining why some contrails form, some aircraft form contrails and some others don't. And what it comes down to is how humid the plume is. So what we've got on this axis here is the temperature on the x-axis, and so right is warm, left is cold, and then the partial pressure of water vapor on the y-axis. So that's the quantity of water that there is in the atmosphere. And what I'm going to put on here are the saturation lines. So the solid line is for liquid. So if you're above that, it's really like humid, right? It feels really humid. So if if you're in a tropical place and you feel like when you're sweating, it's not evaporating, you'd be above that solid black line, right? So that's really humid conditions above that line. And then the dashed line is the saturation with respect to ice. So it happens to be that to get water molecules to adsorb onto an ice surface requires a lower partial pressure than it does onto a liquid surface. And what's critical here is I'm going to show the evolution of an aircraft engine exhaust plume. Right? So it's going to start very warm. Right? In fact, it's going to start way off the screen to the right-hand side because it's really hot. It's several hundreds of degrees Kelvin coming out of the aircraft engine. So it's going to start really warm, and then it's going to go towards the left-hand side, and it's going to cool down as it mixes with the ambient air. And so in this case, in this particular exhaust, it ends up, say, at 230 Kelvin. But in this particular case, there's no contrail formed. Right? And the reason is because it never crosses the solid black line. So it never becomes supersaturated. On the other hand, this orange line does cross the solid black line. So that does become supersaturated, and we'd expect in this case a contrail to form. Right? But then it ends up below the dashed black line. So any ice particles that form, the exhaust is no longer humid enough at the end point for those ice particles to survive. So they evaporate. Right? And so we have to have just the right conditions for an aircraft engine exhaust to form a contrail and for those to persist. So it has to cross the solid black line, it has to become supersaturated with respect to liquid water, and then it has to end, the end point has to be above the dashed line, so it has to remain supersaturated with respect to ice. So we end up with that green area where we form persistent contrails, and the orange area there where we form short-lived contrails. But the critical thing is that we need to cross this line to be supersaturated to even form a contrail. Now, you can play with this, so you can change say that the gradient of this slope, and that will depend on the engine efficiency, the fuel properties, because that determines how much water vapor is emitted by the aircraft engine. So the gradient of these lines do vary depending on aircraft engine technology. Take an extreme example, right? So hydrogen has a lot more water vapor emissions, so you'd be more likely to form contrails, but maybe they won't last as long, right? So going back to this picture, as we are cooling this exhaust, we're generating humid conditions in the exhaust, and we're activating these different particles. And because they're so small, these volatile particulate matter particles in particular, they are a few nanometers in size. So we need really high supersaturation in order to activate those into droplets. And it turns out, if we show this graph, there's a lot of data on here. On the x-axis, that's the soot emissions, the non-volatile particulate matter emissions. So the left-hand side is low soot, might be representative of some lean burn engine technologies today. And on the right-hand side is high soot, which is representative of older engine and combustion technologies. And on the y-axis is the number of contrail ice particles. So at the bottom, we'd have very few ice particles, and at the top, we'd have lots of ice particles and a brighter, more visible contrail. And what we're unpicking here is the dependence on ambient conditions. And you need really cold, well, if you have, let me put it another way, if you have very cold conditions, so up towards the top, those blue lines, you activate more of the particles that are emitted, and you form more ice particles, compared to if you're at warmer conditions, you have a contrail which has fewer ice particles in it. Now this is driven by the ambient temperature to a large extent. So the properties of that contrail are going to depend on both what are the emissions coming out of the engine and the ambient conditions into which those emissions are ejected. So contrail formation requires the jet exhaust to become supersaturated, so that's greater than 100% humidity. And the colder and more humid the plume, the more of those emitted particles will form ice particles. And so what? So not all flights form contrails, right? Because then you need to have the right ambient conditions to form contrails. And even fewer of those flights will form persistent contrails, which are contrails lasting for more than a few minutes. So let's go to persistence, right? So we've talked about emissions and formation. The next stage is, does that contrail persist? So we need to be in the green area where we have persistent contrails, where it remains supersaturated with respect to ice. So we need these what are called ice supersaturated regions. And it turns out that these ice supersaturated regions around the world are highly dynamic, so they move around. They are more likely to occur in some regions than other regions because of global circulation in the atmosphere. And they are also varying in altitude. So the three figures here show the red areas are the ice supersaturated areas. On the left-hand side, that's at 34,000 feet. In the middle, that's at 36,000 feet. And on the right-hand side, that's at 39,000 feet, roughly. And you can see slightly different regions in those three panels. So for instance, on the right-hand side here, we're not seeing as large an extent towards the north of the image as we are in the middle or on the left-hand side. So we know that they vary in space and time, and both in terms of horizontal extent and also their vertical extent. Now it turns out they're typically quite thin, so they're not very deep. These ice supersaturated regions are not very deep. Roughly 80% of them, this is from balloons that are taking measurements of the atmosphere, radiosondes, roughly 80% of them have a depth or a thickness of 4,000 feet or less. And so to put that into context, the sort of typical vertical separation of aircraft is 1,000 feet. So when we talk about vertical deviations, as people will talk about vertical deviations to avoid ice supersaturated regions, they're talking about deviations that are well within the cruise ranges of aircraft today, and on a scale comparable to the separation distance between aircraft today. So people are not talking about kind of flying substantially lower. This is well within the operating range of aircraft. I mentioned that these ice supersaturated regions vary in space and time, and that means that some regions form more persistent contrails than others. Globally, around 5% of flight distance flown forms persistent contrails, but that does vary significantly around the world. So in the North Atlantic, it's more like 10% of flight distance flown forms persistent contrails. In Europe, it's about 7%, whereas in East Asia, it's more like 2%. Right? And that's because of these global circulation dynamics, which means that some parts of the world have an atmosphere that is drier at cruise altitudes than in other regions. This also gives an indication where we would want to focus any mitigation activity of contrails. So, seemingly the North Atlantic, with very high proportion of flight distance flown forming persistent contrails, would be an area to target. So contrail persistence requires the ambient atmosphere to be supersaturated with respect to ice, and these ice supersaturated regions are dynamic but typically relatively thin, so less than 4,000 feet deep. Globally, 5% of flight distance flown forms persistent contrails, but some regions are worse than others. And so persistent contrails could potentially be avoided, and this goes back to what Joachim was saying, could potentially be avoided by minor changes to flight altitudes if forecasts of these ice supersaturated regions were sufficiently accurate. Right? And it's a big if. So we've gone emissions, we've gone to formation of contrails, we've talked about persistence, the conditions for persistence, and then we're interested in, well, what is the effect on the climate? Right, so what is the radiative forcing of these contrails? And if you have been in this field for any more than a couple of weeks, you will have seen this figure probably 10 times already, right? So this figure is from a meta-study by David Lee, looking at all of the different ways that aviation emissions contribute to climate impacts. And it shows all of the different components in terms of an effective radiative forcing. And the statement in the abstract says that the non-CO2 terms sum to yield a net positive warming effective radiative forcing that accounts for more than half, 66% of the aviation net effective radiative forcing in 2018. And if you look at the figure, you can see that the contrail cirrus effective radiative forcing bar here is larger than the CO2 bar. Right? So this is what people use to make an argument that saying we need to work on contrails because the climate effect of contrails is comparable to that of carbon dioxide from aviation. But there's a lot behind this graph. And we're going to unpack some of it. Okay? We'll see if we do a good job. It's worth pausing just to say that there are other impacts. So NOx. NOx has a warming effect because it produces ozone, but it has a cooling effect because it reduces methane concentrations in the atmosphere. So those two provide, it's thought, a net positive warming effect, although there's also uncertainty in NOx. There's water vapor emissions, which are a very small component. And there's some direct effects of the aerosols that are emitted, so both black carbon as the soot particles and sulfur emissions provide a cooling effect. And then they're added up at the bottom here to provide a non-CO2 term and a CO2 term. Okay, so radiative forcing. So what does this mean? Right? So we have the emissions. Generally, this is not just for aviation. We have emissions that change the atmospheric concentrations of greenhouse gases in the atmosphere. Those greenhouse gases can cause a radiative forcing. By definition, they are a greenhouse gas because they cause radiative forcing, which is a change or a perturbation in the Earth's energy balance by that climate change mechanism. So if you have CO2, for instance, CO2 traps some of the outgoing heat from the Earth, so that is a radiative forcing, a positive radiative forcing, a warming effect. Now, if we have that radiative forcing, then we can have climate change, so temperature rise, changes in precipitation, changes in sea level. That can cause impacts, and those impacts cause damages, right, on society, on economies, etc. And so, radiative forcing is quantifying the step kind of in the middle, but actually we're also interested in climate change, right? What are the effects of that radiative forcing on temperature rise, sea level rise, etc. Now, so as we go from left to right, there's an increasing relevance of these stages. Ideally, we would like to quantify damages, right? Because that's more relevant. The issue, though, is that it also is more uncertain. So lots of the kind of IPCC reports report on radiative forcing and climate change, so temperature. And we're going to put that into perspective for aviation. But now, going back to this figure and just focusing on contrails and CO2, we're seeing that this isn't capturing the full climate effects, it's capturing the radiative forcing effects. And there's an important part here as well, which I will come to, which says that it's from 1940 to 2018. Right? So I will come back to that, but what this means, and I'm going to say it here so you can kind of let it sink in, is that this CO2 bar represents all CO2 from aviation between 1940 to 2018. That's all of the CO2 emitted by aircraft in that time period. And the contrails bar represents the contrails in 2018. So behind this figure, there's a lot of stuff, and I will kind of come back to that. But let's unpack the contrails, right? So contrails have radius effects. Here's our contrail, which you can just about see in the picture here, and our sun in the right-hand side of the figure. I could have got one of my sons to draw this, and they would have drawn it like this. So we have a cooling effect because the contrail can reflect incoming sunlight. So it means that there's less sunlight and heat entering the Earth's atmosphere, so that's a cooling effect. And they can also have a warming effect because they trap outgoing heat. So outgoing heat that would otherwise have been escaped and been lost to space is trapped by contrails. And so on net, this is a warming effect over all contrails around the world. That's also because at night time, we don't have the sun shining, and the cooling effect goes away. Right. So the net effect, so the total effective radiative forcing from CO2, all CO2 from aviation, is about 35 milliwatts per meter squared. For contrails, is about 57 milliwatts per meter squared. Total non-CO2 is about 66 milliwatts per meter squared, and the total aviation ERF is about 100 milliwatts per meter squared. The total anthropogenic radiative forcing is more like 3,000 milliwatts per meter squared, which means that aviation contributes to about 3.5% of anthropogenic radiative forcing, and the contrails part of that is about 1 to 2%. So that's where Joachim's statement about 1 to 2% of all human effective radiative forcing is from contrails. So 1 to 2% might sound small, but I'd argue that if we can identify 1 to 2% attributed to a specific thing, and we could do something about it, then it's worth exploring further, at least. And obviously, if a flight was to avoid forming a contrail, then the effective radiative forcing or the trapping of heat wouldn't happen, right? So that heat would escape. So how do we interpret this effective radiative forcing from that Leotal figure? Well, so we have to consider the timescales over which these effects are happening. So CO2 remains in the atmosphere for centuries. It accumulates in the atmosphere. It does decay in concentration, but you can think about it as accumulating. So the CO2 energy effective radiative forcing term represents the cumulative effect, the accumulation of all of the CO2 in the atmosphere from 1940 to 2018. And if we stopped flying tomorrow, that effective radiative forcing from aviation CO2 would decline over centuries. Okay, so it would not go to zero and the heating effect would continue. In contrast, contrails last for a few hours. Right? So the most time a contrail will last maybe 12 hours at maximum, 18 perhaps. And so that contrails effective radiative forcing term represents the average effect of contrails in 2018. And if we stopped flying tomorrow or stopped producing contrails, that effective radiative forcing term would go to 0 within hours, and the heating effect would decay very quickly on a climate scale. Right? So this effective radiative forcing looks back from the past, looks back from present day to the past, accumulates all of the CO2, and looking forwards, the climate impact of aviation contrails in 2018 is comparable to CO2, but the relative magnitude depends on the climate metric that we use. So you'll hear this discussed. So we're going to look at a response of a radiative forcing from a pulse of aviation activity in 1 year. So imagine we could just operate aircraft for 1 year and measure the radiative forcing effect, temperature change due to that. So we'd have a very small bar for CO2 emitted in 2018. And we'd have a big bar for the contrails effect in 2018. Now, some of you might think, oh, that seems really small for CO2. Why is it small? Well, remember that the 35 milliwatts per meter squared of CO2 is accumulated over 1940 to 2018. So it makes sense that any individual year is a small component of the total. Right? And so the radiative forcing, because CO2 stays in the atmosphere, we'd have that every year, right? All the way out to 20 years here I'm doing, right? And so we can then add up all of these bars and we say, well, okay, over 20 years, the sum of the effective radiative forcing from CO2 would look like that. And for contrails, we just take what we had in year 1 and we can kind of compare them. And this is the GWP, the global warming potential, the integrated radiative forcing, or the sum of the radiative forcing over time horizon. And in this case, over 20 years, we see that the GWP for CO2 is less than that for contrails. But you could argue, actually, what we're really interested in is temperature change, right? So the CO2 that is in the atmosphere due to that pulse of emissions, it lasts. So that temperature effect will continue and will sort of stay level over this 20-year period. Whereas the contrails is going to have a peak at the beginning because of the contrails had an effect at the beginning, but it's going to decay after that. And then if we look at 20 years into the future, we see what the temperature effect is in 20 years of those emissions in year 1. We see that there's a difference, right? So the aviation CO2 has a bigger temperature effect in 20 years than the contrails effect did 20 years ago. And so this gives our temperature response in 20 years. So that's the GTP 20. So we have different climate metrics that quantify different things. And so that's where these GWP 20 and GTP 20 metrics come from, and they change exactly how we balance, say, CO2 versus contrails. But really, like, this is a significant thing. The main take-home message is that contrails are a significant contribution of aviation to climate, regardless of exactly which metric you choose. You could choose a different time horizon over which you wanted to look at, so you could look at the temperature change in 100 years, and no climate scientist is going to say, we'll pick one of these, right? Climate scientists will say, well, this is a value judgment, so sort of a political judgment. So there's different ways in which this can be framed. And we know the GWP 100 is very familiar. That's the basis of most sort of protocols on greenhouse gas emissions. But we also know that we have a Paris Agreement which says we want to limit temperature rise in 2050, and so that gives us a sort of 20-year time horizon on temperature rise. And conveniently, GWP 100 and GTP 20 roughly have the same numbers. Right? But the main take-home message is, okay, metrics matter in the case of like looking at the difference between sort of different things perhaps, but it doesn't change the fact that contrails are an important issue. Of course, a pulse emissions is not what we have today, so we actually have this situation going on where we have like CO2 from aviation increasing and accumulating in the atmosphere, and we have this contrails effect, right? So what we're seeing from this is that we'd expect roughly equal or even temperature change due to contrails, and then an increasing temperature change due to CO2 because of the CO2 accumulating in the atmosphere. And this is some very recent work. So what is the temperature change that we can attribute to contrails or CO2? So contrails at the top here in red, or CO2 at the bottom here in 2050. And contrails account for about 60% of the temperature change in 2050. And CO2 is about 40% of the temperature change. Now, we have also looked at what if you do contrail avoidance, but that's a different topic. Very, very early stage work. So contrails account for about 3.5% of human-induced effective radiative forcing. Aviation accounts for 3.5%. Contrails account for about half of aviation's total effective radiative forcing. To quantify the impact of a flight today, we must consider CO2 and non-CO2 in the future and choose a time horizon. But while there can be trade-offs and the relative importance might change, I don't think it changes the main story that contrails are significant. Now, eventually, these contrails disappear, so we have an end-of-life stage, which I'll just skip over. So after all of that, so what, right? So engine emissions are important. Sustainable aviation fuels will not eliminate contrails. They might reduce them, but they won't eliminate them. Not all flights form contrails, and even fewer will form persistent contrails. Persistent contrails could be avoided by minor changes to flight altitude if forecasts were accurate, and there can be trade-offs between different climate forces, so CO2 versus contrails. So, and I would argue, based on all of this, so we know that contrails are important, we know they're a big thing, we need to very quickly find out if contrail avoidance is feasible and to what extent. So, yeah. Joachim, I've got a whole section on what can we do about contrails, but we have fuels and we have technology, right? There's information here on different studies which have looked at this. They back up the statement I've just said that sustainable aviation fuels are not going to eliminate contrails. In fact, maybe globally, if we use them at really high blends, they might reduce contrail radiative forcing by 26%, right? So it's not elimination. When we talk about avoidance or changing of routes, no one is saying that we do that at all costs, right? It has to be within the aviation system where safety is priority, and there has to be a process of learning. We know that there's potentially a fuel penalty, but that fuel penalty is really small relative to the potential benefit. I don't have enough time to explain this figure, but we also have lots of observations that we're using, right? So using observations to measure contrails is a critical part of this. And transparency, provision of data, and forecasts, so people can tear apart that data. We'll come to uncertainty in one of the later sessions. And I think my main point is here that we deal with uncertainty all of the time. There is uncertainty in all of these estimates, in contrail effects and CO2 effects and NOx effects. There's uncertainty in the change in the future as a result of mitigation of CO2 from aviation. There's very large uncertainty in that, right? So we have to have a rational approach and understand that some of these are scientific and some of them are operational. So when people say contrail processes are uncertain, we don't know if any one contrail will be warming or cooling. Okay, there's uncertainty there. We're very sure about nighttime contrails, actually. They're going to be warming. There's uncertainty in emissions, especially VPN. Yes, we need more measurements, but we need to also use observations to look at these differences in contrails. There's a large uncertainty in the effective radiative forcing. Yeah, but actually recent studies and observations have estimated the effective radiative forcing for contrails within the uncertainty range of Lee et al. I don't think we're going to get a really significant change in that uncertainty bound on the effective radiative forcing for contrails. So what are we going to do acknowledging that uncertainty? And I will go through, right? So we've gone through this chain. If we could reduce emissions, we can reduce formation, we could reduce persistence, maybe we can deviate around some of these issues that we're trying to tackle to form fewer persistent contrails that form a radiative forcing. So the final points are contrails account for about 1 to 2% of human-caused warming. Not all contrails are created equal, and that means that there's a large potential, at least from what I can see, for operational avoidance. And we need to work towards real-world demonstrations to tackle complexity, right, the complexity of the aviation system, and uncertainty head-on. It's only until we actually try to do it we understand all of the issues that might crop up. So, thank you very much for listening.
Thank you, Marc. Maybe we have time for one question. Yes.
Thank you very much for a very impressive and very convincing and clear presentation. I really enjoyed it. My question, to be quick, is could you elaborate a bit on why global temperature potential is not the best? You said there was a political weighting of which one you prefer. Could you elaborate a bit on that?
From what I can see, I don't know the ins and outs, but from what I can see is that climate scientists present the information and present it in different metrics, and the view is that, well, it's a political decision as to then which metric to choose and how to weight mitigating one kind of climate forcer versus another, because that mitigation action requires different things to happen. So, for example, mitigating methane emissions requires different actions to mitigating CO2 emissions, and the responsibility changes, right? So who is responsible for doing that is different in those different situations. So the view from at least the scientific community has been present the information and then allow politicians to make the decision. I mean, as an engineer, I think the reality is that politicians don't have time to really understand the issue to make the decision. So we need to guide that discussion, right? And we do have things like the Paris Agreement, which are very clear statements of what we want to achieve as signatories to that Paris Agreement. So if that's the case, we need to understand what the temperature change in 2050 is going to be. Of course, we need to be mindful of what the effect will be after that. We don't want to just meet a temperature target in 2050 and then have emissions increase later on and have uncontrollable temperature rise afterwards. But I think maybe that's sort of a background context.
Okay, one last one here. Very last.
Thank you. Just one question. Looking at the locality of the contrail effect, doesn't that mean that, for example, if you look at the North Atlantic, where a lot of concentration of this effect can be seen, that the temperature rise on the North Atlantic could be much more attributable to contrails than any other thing there?
Very difficult to say. So there have been some studies. You need global circulation models to do that. Because of where the heat is trapped, it's not at the surface level, and so it takes a time for that trapped heat, to move around the atmosphere. So it's not necessarily true that because you have effective radiative forcing of contrails in a particular region, that you also experience the climate change due to that in that region. So there's been a few studies to try and identify surface temperature changes in response to contrails. Kind of been unsuccessful, inconclusive, and it's because you get these that heat moves around the atmosphere in ways that you need models to understand. So it's not necessarily true that the kind of effect or the impact happens where the contrails happen.
Professor Marc Stettler, thank you so much.